Okay, so as the title here says, I'm going to be talking about causal inference on observational data, a new paradigm in earthquake engineering. I don't use the term new paradigm lightly. I really do think that this is a new area of inquiry for the earthquake engineering community. And I also think that it could be potentially transformative. So this presentation is based on a paper that is going to be published in Spectra soon. It's making its way through the production stage. So if the things in the presentation, if you find that they're of interest to you, I encourage you to check out the paper for more details. So I'll start by talking about causal inference. What do we mean when we say causal inference? Then I'll talk a little bit about the relationship of the earthquake engineering community to data and inferring causal effects from data. I'll briefly talk about the broader literature on causal inference and some of the frameworks that I think could be useful for us as a community to embrace. I'm then going to talk about a case study where I demonstrate the application of these methods, and then I'll end with some final thoughts. Okay, so what do we mean when we say causal inference? Well, a good place to start is sort of the obvious, but we get to show a cat photo, so that's always good. Is we can talk about what it's not, right? So we know correlation is not causation, right? As engineers, we've sort of had that hammered into our ears, so to speak, over the years. But more formally, I have a description here that's taken from two scholars that work in this area, Jennifer Hill and Elizabeth Stewart. Causal inference refers to an intellectual discipline that considers the assumptions, study designs, and estimation strategies that allow researchers to draw causal conclusions based on data, right? So the drawing causal conclusions based on data part, that's the part that we're gonna cue in on as we move forward in this presentation. Another way we can give some insight into what we mean by causal inference is to contrast it with some of the methods that we've become used to that are sort of germane to traditional statistics, right? So this slide shows two columns. The one on the right has a set of terms that are associational. So there are terms that are that are permeated traditional statistics. And the one on the left are terms that are used when you are specifically trying to infer cause and effect from data. And I would venture to guess that, again, as engineers who are used to working with data, we're familiar with most, if not all, of the terms on the right, whereas the ones on the left, maybe we've seen them before, but we haven't really sort of engaged with them significantly in our work. So this figure is taken directly from a book by Judea Pearl. So Judea Pearl is a UCLA computer scientist. He's also a Turing Award winner. He's considered one of the pioneers of this field of causal inference. So he produced what he calls the ladder of causation, right? And this ladder has 3 levels. So at the first level is what he describes as the associational level. So here the types of inferences that we make are based on the act of seeing or observing. So what do we mean by that? Well, we mean that when we have data and we try to establish relationships between variables, it's based on saying, okay, if we see this variable, what do we expect to see about, say, another variable, or the effect, or not the effect, but the level for another variable. And I would also venture to say that all of the data-driven models and inquiries that we've done so far within earthquake engineering, including the ones that are sort of machine learning based, operate at this level. The second level he describes as intervention, right? So this is where we try to infer the effect of one variable due to some physical intervention of another. So for example, within sort of seismic risk management, we're often interested in the effect of some physical intervention on seismic risk, right? And so Pearl describes this as in terms of the act of doing, meaning how does one variable change when we intervene by doing something, or we physically introduce or vary another variable. And then at the highest level are counterfactuals, right? So this is associated with activities related to imagining, retrospection, and understanding. I should mention that the higher you go up the ladder of causation, the higher a burden of proof you have in terms of any type of investigation that you're doing at that level. So at the highest level, you're dealing with sort of issues that are related to, for example, if you've heard of the but-for test that is used in the legal environment. So if we can sort of think of a structural engineering example, we can think of the collapse of the building in Miami. It's one thing to say that corrosion was one of the factors that caused collapse, and I'm not saying it was. I'm just sort of making a point here. But it's another to say if corrosion didn't happen, collapse would not have happened. There's sort of a distinction between the two statements. The second statement is a much stronger one that has a higher burden of proof. Okay, so where are we now in terms of the earthquake engineering community and the way that we use data and we try to infer information from data? Well, at this point, you're probably saying, well, Henry, we're used to extracting causal insights within earthquake engineering because, we do controlled experiments that allow us to get causal information. So this shows an image of experiments for steel plate shear wall. And we know that if we want to understand the effects, say, of the yield strength of the steel, we can build two specimens, and the only thing that would be different between the two would be the yield strength of the steel, and then that would allow us to sort of get causal information on how that affects the behavior. We can also do the same thing with engineering models, right? So these are models where we have the ability to exact control in terms of the variables that we change. Again, this shows a steel component connection, and if we wanted to know, for example, how the ultimate strength of the steel affected the behavior, we can sort of tune that in a control way and get that information from our model. However, when we get to data, things get a little bit more hazy, and I'll talk about what I mean by that a little bit later. But that's really where we're going to put our focus. And I also want to mention that for all of these three sources of causal insights, we also have physics, right? We also have a physical understanding. We typically have a physical understanding of the system that we're trying to study that also adds to the causal insights that we can get from these sources. Okay, so what type of data do we work with, and sort of how do we use it? This slide shows is showing data that we get from physical experiments. So as you all know, we have a history of doing physical experiments on systems and components, and over the years we've built up data sets of different types of components with experimental data. And so there's a trend now where we would take that data and fit a statistical model to try to predict some parameter that we can use in our computational model. However, these data-driven models that we develop using experimental data, while they are useful for predictions, they really aren't able to provide quantitative fundamental insights on behavior. And the quantitative there is important because, as I mentioned before, when we build these statistical models, we do so with the knowledge of the physics that drives the behavior that is of interest to us. So there is the argument to be made that the statistical models coupled with our physical understanding of whatever we're studying is enough to draw causal conclusions. But it's one thing to sort of, make anecdotal claims about potential cause and effect and actually quantifying that cause and effect. So just to quickly illustrate, we can consider this study by Professor Wallace and his former PhD student, Saman Abdallah. They collected data on reinforced concrete shear walls with special boundary elements, and they used that data to develop a statistical model that relates different parameters to the drift capacity. This model has now been embedded in the 2019 version of ACI, right? So it's a model that wants to predict the drift capacity of the reinforced concrete wall, and it takes in information on the slenderness ratio of the wall, the shear stress that the wall is subjected to, the compressive strength of the concrete, and the configuration of the transverse reinforcement in the boundary elements. And here they use this alpha parameter that says hoops, which we know are good, which we know provide good behavior, you get an alpha of 60, so you'd get a higher drift capacity. But if you only have single hoopers cross ties, you will get an alpha of 45, right? And so there's quite a detailed discussion in the paper on this study that talks about the benefit of overlapping hoops. It goes back and it points to different individual experiments that demonstrate that, and our physical understanding of shear wall behavior to demonstrate that. But that causal relationship was not quantified as part of this study. And so part of what I'm advocating for is the adoption of methods, tools, and also language that will allow us to answer those types of questions. Another type of data that we often work with is field reconnaissance data, right? So this is after an earthquake, we go out, we collect data, and we use it for different reasons. We use it to develop fragility functions, do statistical analyses. These days, we're doing a lot of machine learning models, and also we use it to get anecdotal insights. Now, as I said before, and as you'll keep hearing me say, these statistical models, even the machine learning ones by themselves, cannot be used to infer cause and effect. So one thing, if you go through the literature on sort of these field reconnaissance studies, you would find that the investigative findings tend to be either what I call anecdotal or correlation based. So to give you an example, this image, I think, at least within the earthquake engineering community, is now pretty famous. It's taken of two houses that sort of stood side by side after the 2014 South Napa earthquake. One of them had, so these are single family buildings. One of them had the cripple walls retrofitted, and the other did not. And as you see here, the retrofitted building performed much better. And again, these sort of reverse the orientation to get it to fit on the slide, but these are buildings that are right next door to each other, right? So so this image has been widely used as sort of evidence for the benefit from retro. Yeah, if indeed, I think there is an argument to be made that the building on the bottom benefited from retrofit. After all, the two buildings were sort of, for all intents and purposes, at the same site, so they probably experienced the same shaking intensity. But for one, it's just one observation basically. But two, we're still not okay. So you can argue that they saw the same shaking intensity, but there are other variables that we know could affect the performance that we were not able to compare between these two buildings, right? In another type of investigation, so this particular study was done by geotechnical engineers. They hypothesized that the distribution of damage after the 2014 Napa earthquake was partly driven by the sedimentary basin below the city. And so they did this study that was statistically driven, but really the only thing they could conclude is that the red and yellow tags were correlated with the age of the building, and it was also correlated with the underlying sedimentary basin. They couldn't really make any strong causal conclusions from their data. This is another type of study that or another way we use data in the earthquake engineering community. So we perform numerical simulations. Here I'm focused on a specific type of simulation, and I'll get to why that is a little bit later. But I'm focused on simulations where the goal is to quantify the effect of some ground motion parameter on structural response or performance. So parameters such as ground motion duration, the presence of pulses, basin effects, or spectral shape. Now, simulation data is interesting because in some cases we can mimic controlled interventions, right? So I showed that slide earlier of that connection and the finite element model of that connection, and I said if we wanted to evaluate the effect, say, of the strength of the steel, we can sort of tune that in a way that allow us to get causal information about that effect. However, when you start talking about studies that quantify the effect of ground motion properties on response and performance, we often cannot conduct a well-controlled simulation experiment because the variable that is of interest to us comes from the ground motion, and the ground motion is not something that it's in the category of observational data. It's not something that we produce. It's something that's produced by the earthquake. And we are not able to sort of tune ground motions in a way to sort of vary one type of parameter without doing another. I mean, maybe we could do that, but obviously we know that that will create more issues than problems that we would solve. And so we end up relying on statistical analyses and results such as correlations and hypothesis tests to draw our conclusions, which, as I said before, cannot give quantifiable causal insights. Okay, so the last category of data I'm going to talk about is response measurements, right? So these are buildings that are instrumented with accelerometers. We're able to measure the responses, and we use this data for a number of things to do response reconstruction, system identification, model updating, damage assessment, and so forth. Like the experimental data, we often use response measurements. We often use response measurements to construct predictive models. These models provide value in terms of they enable predictive assessments, but they're very limited in their ability to inform causal conclusions. And so one of the things that I've been thinking about is sort of where do we stand as a community, like our relationship to using empirical data to draw causal conclusions. And I came up with this term. I call it the curious case of causal thinking but associational effect quantification. So what do I mean by that? Well, I showed this figure before that shows that regardless of the source that we draw on to get causal insights, it's always underpinned by our physical understanding of the system. So it's often the case that when we do these data-driven investigations, we're able to sort of justify causal conclusions based on, our understanding of physics and anecdotal evidence and so forth. But we often have to fall back on using associational metrics to quantify the effect. So now I'm going to highlight a couple of studies that are sort of in this vein. So this particular study was done by Professor Miranda at Stanford and one of his former PhD students. they were interested in the effect of spectral shape on structural collapse. And so this is a key result that they have. So they have this plot showing the horizontal axis spectral shape, the vertical axis some measure of collapse. It's log transform. You have a nice sort of linear trend. And so they report, R-squared values and correlation values as sort of results demonstrating the effect of spectral shape on collapse. Now, what they did not do is look at other variables that are sort of embedded in those ground motions that could also influence collapse, right? So this is the idea of confounding that I'll talk about a little bit later, right? But again, we know from structural dynamics that spectral shape reflects the frequency content of the ground motion. And so we do expect it to have some effect on the performance. But again, when we move to quantify that effect, one, we're not rigorously dealing with this issue of confounding, but also we're quantifying that effect in a statistical way. This is another study that was done by Abby Lyle and her former PhD student, Meera Raghunandan. And here they were interested in the effect of ground motion duration on structural collapse. So this was another interesting study. There was a really great write-up that talked about the fact that there's this thing called cyclic degradation, which means that if you cycle a component back and forth, even if you don't change the amplitude, you will see some degradation because of energy dissipation. And so if you have a ground motion that has a lot of cycles, which is typically the case in a long duration ground motion, we do expect that it would affect the collapse performance. And the results of our study demonstrate that. But again, the results of the study are presented in terms of sort of these statistical metrics, correlations, R-squared values, and hypothesis tests. This particular study is quite interesting because, so this is a study that was done by Regan Chandramohan. So we were PhD students together at Stanford together. He worked with Jack Baker and Greg Dearline, and they also were interested in the effect of duration on structural collapse. But they actually recognized, at least in some sense, this issue of confounding, right? So they said, well, we know that duration is not the only ground motion parameter that affects collapse. We actually know that spectral shape also affects collapse. So what we're going to do is we're going to create two sets of records, one with long duration motions, one with short duration, but we're going to make sure that they're spectrally equivalent, right? So we're going to make sure that the variable, the confounder, if you will, in this case here, the spectral shape is the confounder. We're gonna make sure that the confounder is well balanced between the two sets of ground motions. That way, we can sort of isolate the effect of duration on collapse. Now, it's interesting that, I know that these authors, they weren't and aren't familiar with the causal inference literature, but sort of their intuition as sort of investigators sort of led them to think about this issue of confounding and try to address it as best as they could at the time. Okay, so now I'm going to talk really briefly about sort of the broader causal inference literature, and I'll sort of tie it back to stuff that we do. So what I want to do first is sort of describe what I call the anatomy of a causal inference problem, and I'll sort of frame it in a way that we as structural engineers, earthquake engineers can figure out. Right, so we say that the goal is to evaluate the effect of some treatment, and we're denoting that treatment as D. And in this case, we're going to say our treatment is seismic retrofit, right? So we were going back to Napa. We're going back to say, okay, maybe there is a way we can collect data that allows us to say on average, what was the effect of seismic retrofit on cripple walls, not just for a single building, but for sort of the entire population of affected buildings. Right, so here we say the treatment is the seismic retrofit, and then there's also an outcome variable. In this case, in our example, the outcome variable would be the earthquake damage. Now we have multiple units, right? So each building is a unit, and each of these units were either exposed to the treatment, meaning in our case it was retrofitted, or it was not. And if it was not, that means it was unretrofitted, right? So the D equal to 1 means it was treated or retrofitted. D equal to 0 means it was not treated or not retrofitted. Now, One issue that sort of really makes this causal inference problem interesting is the fact that, you know, the retrofit state and the damage is not the only variable we have to be concerned about, right? So each unit is associated with a set of covariate variables, right? So these are variables that are not necessarily of primary interest to the study, but they can also affect the outcome. So these are the so-called confounders. So here I'm using age and PGA as the so-called confounders. The other thing that makes this problem challenging, right? If we could have created a world, nowadays there's a lot of talk about multiverses. If we where, okay, earthquake happens, we have the retrofitted buildings and their level of damage. If we could have created a world where we could create exact versions of those buildings that were unretrofitted and have them subjected to the exact same earthquake, that would solve all our problems. But you know, we don't live in the multiverse, so we have to fall back on sort of the causal inference literature. Just as a quick aside, this figure is called a directed acyclic graph. It's called directed because of the arrows. They show conditional dependence or influence, and it's acyclic because you don't have any cycle, so you never start from one node and a cycle would bring you back to the other node. I talked about Bayesian networks in a previous presentation. So a Bayesian network is a type of directed acyclic graph or DAG. Okay, so not going to get into any of the details, but there are causal inference frameworks that are in the broader literature that can be used to address the types of questions that I sort of alluded to throughout this presentation. Again, I'm not going to go into the details of them. If you're interested, I discuss these methods in much more detail in the paper. Okay, so now I'm going to do an illustrative case study where I'm going to look at this issue of the effectiveness of different ground motion intensity measures. So if you've sort of done a lot of nonlinear analysis and you follow the research, you know that there's been many studies that have investigated the relative effectiveness of different ground motion intensity measures. Typically, what they do is they use two criteria, or these are the two primary criteria: efficiency and sufficiency. Efficiency just says the IM that produces the smallest dispersion in our response is the most efficient and therefore the best in that context. And sufficiency is a little bit more complex. Sufficiency says you want an IM that if you condition on it, it's the responses that you get would be independent of those upstream variables that went into producing that IM. So things like the earthquake magnitude and distance and so forth, right? In this particular study, we're going to use a causal inference approach to evaluate the IM effectiveness. And we were able to show that this approach produces results that are aligned with our physical understanding of the problem. Okay, so we want to view our IM-EDP relationship through a causal lens. IM is the intensity measure, EDP is the engineering demand parameter or response. We want to view it through a causal lens, right? So in nonlinear response history analyses, we are typically interested in the distribution of EDP's condition on the IM, right? But we know that the IMs are influenced by a set of upstream or causal parameters like magnitude, distance, rupture mechanism, and so forth. Now, ideally, we want the EDP to be independent of the causal parameters, right? So this is what the sufficiency evaluation attempts to do. So we want the EDP to be independent of these causal parameters after we condition on the IM, but we know that for the most part, if not in all cases, the causal parameter does have an influence on the EDP even after conditioning on the IM. And then there are other factors that we need to be mindful of. So factors that are not of primary interest to the study, but could also be confounders, right? So we need to keep those in mind. But here I'm just showing the magnitude as the only confounder for illustration. Now, in causal language, what we say is that the IM partially mediates the effect of the causal parameter, meaning that the effect of the magnitude on the EDP partially goes through the IM, but there's another part of it that goes directly from magnitude to EDP, right? So in our causal framing, we say that the most effective IM is the one that maximizes the mediated effect, right? Because remember, we're using the IM in our analyses. So ideally, we want an IM that would maximize that mediated effect, minimize the direct effect of the causal parameter on the EDP. In other words, we say the most desirable IM is the one that maximizes the theta M. So theta M here represents the mediated effect of the causal parameter on the EDP, and theta D represents the direct effect. So we implemented this causal evaluation on 5 steel moment frame buildings ranging from 1 to 19 stories. We considered story drift ratios and flow acceleration as the EDPs. We considered both the maximum response over the height as well as the full profile response. And we used a set of ground motions that were put out by Professor Miranda a while ago. And we consider magnitude and distance as the causal parameters. We also did efficiency and sufficiency-based evaluations for comparison. The method that we use is in the category of what's called semi-parametric models. More specifically, it's referred to as double machine learning. In the interest of time, I'm not going to go through the details, but the paper that sort of develops the method is shown in the slide. Okay, so these are some results from the study. So these are actually efficiency results, right? So we're going to start with efficiency. So here we have 4 different IMs: PGA, PGB, SAT1, and SA average, and we have 5 different buildings, right? And so here we're looking at the dispersion for the maximum peak story drift ratio and PFA, right? And so the best IM would be the one that has the lowest dispersion. And so here we see the ones highlighted in yellow are the best IMs in specific cases. So for example, for the 1 story, SAT1 is the best IM. When you go between 5 and 14 stories, SA average is the best. Then at 19 stories, PGA kicks in. For PFA, it's a similar trend. This is the result of a sufficiency-based analysis. Here we're looking at the sufficiency with respect to magnitude. And, you know, without, again, in the interest of time, I would just say that there's no sort of clear trend. So let me go back here, right? There's somewhat of a trend that's sort of consistent with our physical understanding in the efficiency-based assessment, meaning that because we know that PGA performs well for first mode dominated structures, right? That sort of makes sense from a dynamics perspective, but also intuitively. And that's why we have our 1 story building having the lowest dispersion. And then once you get to taller buildings, SA average, which considers a sort of a spectrum of periods, it's the geometric mean of the spectral intensity over a range of periods. So once you get to taller buildings, then the SA average kicks in. However, for sufficiency, there isn't really a clear trend that I can point to that sort of can be explained by our sort of understanding of the problem. This slide shows the causal inference results. So here we're quantifying that mediated causal effect. And so the higher that mediated causal effect, the better. And so again, here we see a trend that's even clearer than the efficiency-based assessment. We see that for the 1 story building, PGA works well. Again, 1 story building, first mode dominated. We expect PGA to work well. But also, you should keep in mind that it's actually quite comparable with SA average. Even though I'm highlighting the PGA here, if you look at the SA average number, it's actually quite comparable to the PGA for both story drift as well as peak flow acceleration. And then once you get to taller buildings, then SA average turns out to be the better PGA. I mean, the better IM. Now, the previous results, the results from the last 3 slides are based on looking at just the maximum response over the height. We also wanted to look at the full profile response to see any trends there. And so here what we're looking at Here, what we're looking at is the efficiency profile for the 5, 9, 14, and 19-story buildings. And what we see is that, and this is for story drift. So what we see is that PGA works the worst throughout the full profile. We see that SAT1 and SA average are sort of competing with each other. PGB also gets in there. But an interesting trend is that when you move up the height of the building, you actually see the higher up the building you go, that SA average starts to dominate as the more efficient IM, right? And the other more interesting thing is that as you go to taller buildings, the height at which, or the portion of the height over which SA average is dominating actually increases, right? So we know that in taller buildings, we're more likely to see higher mode effects. We also know that those higher mode effects are more likely to sort of manifest as you go up the height of the building. So this result is consistent with our understanding. This one is the same plot, but for PFA. So what it shows that, again, the PGA here is the blue line. So at the lower stories, PGA is actually the most efficient, but when you get in the upper portions of the building, PGA is actually either comparable to or worse than the other IMs. And the other interesting thing is that the taller the building, the greater the height over which PGA is comparable to the other IMs, which again is consistent with our knowledge that taller buildings are more susceptible to higher mode effects, where it's responding to different periods. So therefore, IMs like SA average would tend to do a better job. I'll just quickly show the sufficiency results. You don't really see any clear trends going over the height, right? This is for drifts. This is for flow acceleration. For the causal inference results, the trends are there and they are very clear. So for example, so again, these are causal effects. So the higher the number, the better the IM. And so one of the things we see is that, well, the first thing we see is that the distance in terms of causal effect between SA average and the other IMs is actually increases over the height of the building, again, which is consistent with our understanding. And also that distance also increases as you go from, say, the 5-story building to the 19-story building, right? So the difference between the causal effect for, say, SA average and PGA is much higher in the 19-story building than it is for the 5-story building. When you get to PFA, we see something interesting. So for the 5-story building, PGA is actually competitive at the lower stories, but as you get up to the upper stories, SA average is more competitive. But then as you get to taller buildings, PGA could barely compete even at the lower stories. Okay, so I'll end with some final thoughts. So what I'm trying to do here is advocate for a paradigm shift in our domain, earthquake engineering, where we adopt the language, tools, and models that have been developed and continue to be developed in causal inference. I have some specific reasons for that. I think it would bring much needed clarity and transparency in data-driven investigations, right? I talked about that issue, that curious case of causal thinking and associational effect quantification. I think we'd sort of bring a lot of clarity to what we're actually talking about. Are we talking about causation or are we talking about correlation? I think adopting these methods would allow us to do that. I think I truly believe it'll open the door to some new and interesting research questions. I also believe that causal investigations are much more amenable to discovery relative to associational. And I think we'll be able to leverage an unrealized benefit of machine learning models. I didn't talk too much about the details of the methodology that I adopted, but it did involve using machine learning models to control for those confounding variables. Professor Pearl, who I mentioned is a computer science professor here at UCLA, he talks about starting a causal revolution. So here I'm inviting you to join that revolution. All right.